Do you know about gear modes? Just like your car has gears, Intel CPUs also have gears. But what are they, and why might you use them? Let's find out.
Hey everyone, I'm Trisha Hirschberger, and this episode we turn to Intel gear modes, which have been around for a few years now. Let's get our teeth into this before I run out of gear puns. Intel first debuted gear modes in 2021 with the 11th generation Rocket Lake processors. These gear modes are the clock speed ratios of the memory controller inside the CPU to clock the speed of the RAM. Gear 1, also known as 1-to-1 mode, means the memory controller runs at the same speed as the RAM. While Gear 2, or 1-to-2 mode, means the memory controller runs at half the speed of the RAM. And Gear 4, or 1-to-4 mode, runs at a quarter of the speed. This allows the memory and the memory controller to operate at different speeds, enabling support for faster RAM while still maintaining system reliability. It's important to note that by default, the BIOS automatically selects the appropriate gear mode, but users can manually adjust it if needed. Overclocking to reach high speeds, such as 3600 megatransfers per second in Gear 1 or 9000 megatransfers per second in Gear 2, requires a high-quality CPU and motherboard to ensure signal stability between the processor and memory. There are two major factors that come into play with gear modes: memory bandwidth and latency. Memory bandwidth is the maximum rate at which the CPU can read or write data, while latency is the delay between a CPU requesting data from the RAM and the time that data is made available. In higher gear modes, the integrated memory controller on the CPU, or IMC, can potentially become a bottleneck since it can only process data at a fraction of the memory speed, which can cause higher latency. In some cases, staying in a lower gear mode with lower latency may be beneficial. For example, first-person shooters demand low input lag and more frames per second, so a lower latency could be preferable to more bandwidth. On the other hand, for workloads that prioritize data throughput, such as AI processing, video editing, or 3D rendering, higher memory bandwidth may be more advantageous, even at the cost of increased latency. So let's run an experiment. We'll have the same memory running at two different frequencies and see how they're affected by gear modes. For this comparison, we'll use the same DDR5 8800 memory kit in both tests. To ensure consistency, we'll overclock to 9600 megatransfers per second for the second benchmark. This allows us to isolate the impact of gear modes while keeping the DRAM itself constant. Okay, in our AIDA 64 memory benchmark, the DDR5 8800 memory in Gear 2 beat the DDR5 9600 in Gear 4 in read, write, and latency. Why did this happen? Remember, in Gear 4, the memory controller operates at just a quarter of the memory speed, limiting its ability to utilize the available bandwidth to the fullest. The 8800 megatransfers per second kit had 14% lower latency, which is essential for responsiveness in applications like gaming. This just goes to show that raw speed isn't everything. Lower latency and better IMC efficiency often delivers more tangible performance benefits, especially when handling tasks where low latency is a priority. Hopefully you understand a little more about how gear modes influence performance now. Which memory configuration will maximize your system's potential? Are you going to join the gear modes revolution, or are you in neutral about it? Oh, come on, that was my last pun. Thanks for watching, everyone, and I will see you next time with more DIY in 5.